Okay, so in physics, when we talk about work done, it's a little bit different to what work means in the everyday world. So normally, work is when you do something, and to an extent, it's the same in physics, like you've got to do something to do work. But in physics, the definition of work done is energy transferred. There's two actually, so it equals the energy transferred. So whenever energy is transferred from one store to another, work is done. Now, specifically at GCSE and generally, when we're talking about work done, we generally mean mechanical work done, and that happens when a force moves an object through a distance. So if you look back to the energy transfers video, whenever we talk about mechanically transferring energy, that's when mechanical work is done, or we sometimes call it by forces because a force is moving an object through a distance. There is electrical work that can be done. That's when a potential difference moves a charge through a distance, but we don't really look at that too much right now. We're looking at mechanical work. Now, there is an equation that governs this, as always, and the equation for work done, I'm going to write it in full, is that work done equals force times distance. Now the distance isn't as simple as just the normal distance, it's the distance that is parallel to the force. Or you might see this written as in the same direction as the force. I prefer parallel for reasons that will hopefully become apparent later on. So we can write it as a symbol, W equals FD, and I often do a little sign like this to remind myself that it's the parallel force or in the direction of the force, and that becomes quite important. So the unit of work done, there's actually two that we can use that are equivalent to each other. So because work done equals energy transferred, it's a bit of a strange equation this because it's just got one thing on each side, then we can use the unit of the joule, and that's the most common one to use for work, the joule, because energy transferred equals joule, so work done must be the same. But if we look at this equation here, then if we think about the units of force and distance, the unit of force is the Newton and the unit of distance is the metre. So we can say that work done is also measured in Newton meters. So the joule and the Newton meter are what we call equivalent units. Okay, so we're going to have a look at 5 different problems here to try and explore this equation. And we're going to start with the simplest one really, when I lift an object or a mass up vertically. So I'm going to work out what is the work done when I lift a 2 kilogram mass up 3 meters vertically. Now whenever I lift something, the force that I'm working against is the weight of that object, or I'm working against gravity. Now gravity acts downwards, so the distances that I care about are the vertical distances, because downwards, parallel to that is up or down. That's why I like the word parallel, compared to in the direction of. So I care about any movement vertically up or down. Now I'm going to work against gravity here, so because gravity is down, I'm going to go up. Now the work done equals the force times the distance, but the force is not 2 kilograms. The force is the weight of the object, so the force actually equals mg, the weight of the object. So the work done is the weight, which is 2 times 10 meters per second squared, or 10 newtons per kilogram, is the acceleration due to gravity, or the gravitational field strength of the Earth. You might use 9.8, you might use 9.81. For our specification that I teach, we use 10. And then multiply that by the distance, which is 3 meters. So the answer, 2 times 10 times 3, comes out as 60 joules. So the work done here is 60 joules. Now just as a little bit of a pointer, this equation here is where we get the Gpe equation from. So if we think about the fact that I've said force equals mg, well, I could then call the distance, because it's moving vertically, a height, and mgh is equal to Gpe. So this is where the Gpe equation comes from. Gp equals mgh because work done equals force times distance. It's a specific version of the work done equation. Here I've got a block and I'm going to move it 3 meters sideways. Imagine that you're holding maybe a 2 kilogram textbook, quite a heavy textbook, but you never know, and you want to just move it sideways for 3 meters. How much work would you do against gravity? I'm going to think about here. Well, work done equals force times distance, and that distance has to be parallel to the force. Now if I care about gravity, which is acting downwards, the parallel distances are up and down. 3 meters is perpendicular to that force. So in terms of the parallel distance, it actually doesn't travel any distance at all. So even though the force is 2 times 10, 20 newtons, the weight, it doesn't travel in that direction. So in this circumstance, very strangely, you might feel, the work done on the object is actually 0 joules. So that object doesn't have any more energy than it used to have because you've moved it sideways. If you lift an object up, you've given it GPE, so you've given it more energy than it had before. That's what the work done is. But if we move it sideways, not the case. Now your arms might have done some work because you know mechanically and chemically you've had to keep your arms up, but that's different. The book or the block, the 2 kilogram mass, doesn't have any more energy, so no work is done on it. The difference, though, we can still do work horizontally, but here, for example, I've got my 2 kilogram block and it's on a surface. It's on a table or the floor or the desk. I'm going to push it. When I push an object, I will also always have friction pushing back in the opposite direction. Friction always acts in the opposite direction to motion, so it's always parallel to that motion. So here, the work done against friction in this circumstance would be the force, which is 5 newtons. It's not the weight I care about now, it's the friction. So the force that I'm working against, 5 newtons, and the distance is 3. So the work done here would be 15 joules. So it's always important to figure out what force you're doing work against. Is it weight? Is it friction? Is it something else? And then the direction you care about is parallel to that force. So for weight, it's up or down. For friction, it's along the surface. Now we can put all this together here in this example. So here I've got a block that I'm going to push up a slope. And work will be done. And work will be done in 2 ways. I'm going to do work against gravity. And I'm going to do work against friction. And I have to think about them separately. Then I can add them together if I want to. But the work against gravity is going to equal the force, which will be the weight, times the distance that's parallel. So I care about the vertical distance. So here, the weight of this object is 2 kilograms times 10 to get 20 newtons, and the distance it travels vertically is 3 meters, just like before. So here, I'm going to have 60 joules of work done against gravity. Even though I'm going up the slope, it doesn't matter, it's a vertical distance I care about. Then, in terms of friction, the work done is going to equal the force of friction times the distance it travels parallel to friction. Now friction is that way, so I care about this distance here, the distance along the slope. Now this gets a little bit tricky. The frictional force here is 5 newtons, and the distance, well, I haven't got the distance, but I can work it out. If I know that this is 3 and this is 4 meters, I can work out this distance, the hypotenuse, using Pythagoras' theorem. So the square of the hypotenuse equals 3 squared plus 4 squared, or I can get the question mark, I wouldn't usually use question mark, is the square root of 3 squared plus 4 squared. Now that's the square root of 9 plus 16, which is the square root of 25. Therefore, this is a common triangle, a 3, 4, 5 triangle. So the distance is 5 meters, and here, because I'm travelling further and pushing it further than I did there, the work done would be 25 joules. And I could add them together if I wanted to get 85. One kind of tricky example that often comes up is trying to relate work done to kinetic energy lost when you've got a car that is slowing down. So if you ever see a question that talks about braking force and stopping distances, so we've got here braking force and stopping distances, you're probably going to want to use this approach. So a 300 kilogram car has a maximum braking force of 1200 newtons. If it's travelling at 20 meters per second, what is its minimum stopping distance? So here, what we need to think about is what's going on in terms of the brakes. So when we stop a car, we put our foot on the brake, which causes friction between the wheel and the brake, which slows the car down. So what happens is that we lose Ke. The kinetic energy goes from a value to when it's stopped, nothing. And that Ke has to go somewhere, and that kinetic energy is equal to work done by the brakes. So we get this equation, 1/2 mv squared, the kinetic energy that the car originally had, all of that is going to have to go into work done by the brake, so force, we call this the braking force, times by d, which is the braking distance. I should probably have called this here, sorry, the braking distance. The stopping distance has also got a thinking distance in there. And I can put my numbers in and find it out. So I'm going to work out the kinetic energy first. So I've got 1/2 times mass, which is 300, times 20 squared. And that comes out as 60,000 joules. And that's going to equal the braking force, which is 1200, times the distance, the braking distance. And if I rearrange that equation, D equals 60,000 divided by 1200, I get a distance of 50 metres, which seems pretty sensible for a car question. But this is quite a common tricky question that they can ask. So they're thinking about using work done and applying the work done to how much energy has been lost when a car or another object stops. So that's work done. Next we'll go on to power. So move on to the next video if you want to look at that.